points for how we do calculations for two source interference. So like trying to find the location of maxima or minima that are formed. We've got two source interference, and two source interference, well, you could have like two independent light sources, but because the spacing between them, if we're talking about light, is generally really small, what we normally do is have a double slit, and that distance between those slits is really small, like less than a millimetre, for us to see any big effect kind of in everyday life. And so two different pictures, because this picture here, we kind of zoomed out of it, like you can see the double slits there, and in the distance, this black line here represents our screen, and in the centre of the screen, this is where the maxima, the central maxima, the 0th maxima would form, and the X up here, the blue X, represents like the point that we're interested in, which could be another maxima, could be a minima, and the blue line is showing the path that's followed by the light from the slits to that point. When looking at this diagram, you can see I'm just pretending that the slits are just one light source. So that distance there is really big compared to the distance between the slits. And that means that even though we know in reality we're going to have two slits and they're going to converge on something, because that distance is so big, back here we can treat those two rays that come from each of those slits as though they're parallel lines. Yes, they're converging, but the distance between them is less than a millimetre, and the point that they're going for is many metres away, and so effectively they're two parallel lines. What's really useful about looking at it that way is that we can draw a right-angled triangle like that, and we can see that that little chunk down the bottom there is the extra distance that's been travelled by the light from the bottom slit that hasn't been travelled by the light from the top slit. We call that extra distance the path difference. Yeah. What? So we can draw that picture.
Talked about it last year and last lesson.
And from that picture, we can kind of have a look along and be like, oh yeah, that's the angle up to that point of interest. And if that angle there's a theta, then that's 90 degrees. That bit there has to be 90 minus theta, and that means that that bit there must be has to be theta again.
Yeah.
And this bit of the triangle here, the hypotenuse, is the slit spacing. And so check this out. From that triangle, we can see that the path difference, that little difference in distance there, we know the hypotenuse, we've got an angle, we're trying to find the opposite. We can see that the path difference must be equal to d sine whatever that theta is. We know that for a maxima to form, what does the path difference have to be for a maxima? So for a maxima, path difference is equal to n lambda, where n is 0 or 1 or 2 or 3, any of those numbers. And for a minima,
Isn't it n times lambda minus a half?
Yeah.
Was it the other way around?
N minus half.
Yeah.
where n can't be 0, but it can be 1 or 2 or 3 or any of those numbers. And so, hang on, we've got two different equations for path difference here. Over here, we can see that path difference is n lambda for a maxima. And over here, we can see that path difference is d sine theta.
No.
And so for a maxima, n lambda is d sine theta, and that one's so important, you're going to see that one published on your formula sheet. The one that you might have to remember how to make, if you've got that one, is the n minus a half lambda is d sine theta. That one's not on your formula sheet, so we'll put a different coloured box around it just to remind you that that doesn't come on the formula sheet. And cool thing about these equations is they're all just about distances, eh? We've got the wavelength, which is in meters. N's just a number, any number. 1, 2, 3, 4, 5. D is just a distance, and sine theta is going to be a ratio of a couple of different distances, so that's going to just be a number. So it's just distance equals distance equation. If we wanted to use that to solve problems, we'd come back to this right angled triangle here, and we'd be like, damn, we've got the angle in the middle, we've got the L at the bottom, and the X up the side, and so we can use that triangle to solve problems about, gosh, that X is really badly drawn, isn't it? Sorry. It's like, that's the X from the central maxima. The central maxima is there, so the X is the distance from the central maxima to the point of interest, whatever that point is. Is it the maxima, is it the minima, whatever you're trying to find. And so we can use that triangle. We've got the X, we've got the L, we can find the angle, and then we can apply that triangle to solve any problem.
Wait, what?
Like generally the way that you would use this in life is you'd have a couple of slits, which you know the distance between them because you've made them, and you'd fire some light through it and measure how big the angle is to a maximum, and then you can use that to calculate the wavelength of the light. So the reason that this is really useful is this lets us, by firing light through a pair of slits that we've made that spread the light out into bright spots and dark spots, we can use that to measure the wavelength of light, which is quite useful. And then once we know the wavelength of light, we can fire it through some slits, and we can use this to measure the size of the slit. So we can use this to make measurements of really, really tiny little things that we shouldn't normally be able to measure just using a ruler.
True.
I'm fully comfortable with that exercise.
Yeah.
What were you going on about with the X and the distance? And
Why do
that
you need to
stuff?
measure
What was that?
So over here we've just got a right angle triangle. So if I redraw it really basically, there's L, that's the distance from the slits to the screen.
Yeah. Why did
That's X, that's the distance from the central maxima to whatever maxima you're trying to find.
Yeah.
And that's the same angle as over here.
Yeah. No, yeah. And what?
That's it.
That's it.
That's it. We can. So if we use this equation to find the angle,
Yeah.
we can apply that angle over here to find the X or the L. We could use the X and the L from here to find the angle, and then pop that angle into this equation.
Yes, okay. Okay. Yeah.
Things that you
Sorry.
The section of the top of the triangle.
Okay, so if this one is theta, how big is that total angle there? 90. So this one here must be 90 minus theta. And if that's 90 minus theta, that's 90. What's our total triangle add up to?
see it.